Hello, everyone. This is André Fauteux of La Maison du 21e siècle, 21st Century Housing Magazine. And today I'm with Tim Schoechle, who's in Colorado. How are you, Tim?
Great. How are you, Andre?
Excellent, excellent. It's very nice of you to be with us for our Energy Efficiency and Transition Summit. We're recording this ahead of time, April 5th, and it's fitting that we're doing this in the middle of an ice storm in Quebec on April 5th. So just before you start, I'd like to present Tim, who is a pioneer in home automation since 1983 and founder of CyberLinks Gateway Corporation. Tim is a pioneer in home automation who has been in the communications and computer engineering field since the mid-70s and really heavily engaged in standardization since the early 80s in a variety of both expert and leadership roles. A Ph.D. in communication policy, Tim is active in various international standards, educational, and research initiatives, including the International Journal Standards Research. And he served as secretary of the ISO, International Standards Organization Committee on Home Electronic Systems and Home Automation since 1990, as well as in Energy Management Committee. So Tim finally has developed, played really pioneering roles in many technologies such as microprocessors, home networks, barcodes, RF identification, and voice over IP, internet, and energy systems. He served as the University of Colorado Boulder College of Engineering faculty, where he created and taught one of the few standards courses in the world and played a key role in founding its standards research center. Tim's main activity is as consultant, advising governments, organizations, and law firms on standards policy and patent issues. So today I will launch your PowerPoint. Tim is going to talk about reinventing electricity. And I will just correct this. So you have 40 minutes, sir.
Okay. Well, thank you, Andre. This I prepared. This presentation today is really the third part of a series of a three-part series that I have put together on relating to electricity and the future of energy. Part one was on climate change. I presented that last year at the University of Colorado. That's an overview of the climate warming and its consequences and why we really need to change our energy system. Part two is a work in progress right now. It isn't finished yet, but it's about this actual structural transformation of how we would go about changing energy and electricity to transform that system. And then the final part, which we'll be talking about today, is reinventing electricity. It's actually how you do it. One of the methods of decentralized, which consists of decentralization with solar plus storage and microgrids. So the dominant theme here is at the top here. It says localization of energy, localization with solar storage and microgrids in particular. But the key takeaway is that it's about the benefits of localization of energy now that the technologies are available to do that. And especially local energy management. That means managing electricity on the premises, not in a utility or in some distant place, but where it's actually used. Now, and what I'm talking about is not just a transition, but a structural transformation of the energy system from a centralized to a decentralized power system to distributed energy. That's the term that we use. Renewable and sustainable solar PV for self-consumption. In other words, not to sell back to utilities and primarily, but to use it yourself. Produce a solar on the premises where you live and then or work, and then you use it there, and then any you can trade any that's left over with the neighborhood. And the benefits are that you can use we can go to a renewable and sustainable solar system for self-consumption. And the main benefit is resilience, the electricity when the main power grid may fail for whatever reason, or disconnect for some other reason. It's essentially inverting the grid, a bottom-up view starting at the home instead of starting at a power plant somewhere. It's a view. It's just a way of looking at the system. Premises architecture is based on solar plus storage and resilience, generating electricity as close as possible to where it will be used. That's the basic principle. Generate electricity as close as possible to where it will be used. And what the technology that I will be offering is called EMMA, EMMA, which is the missing piece for local control. We have the batteries and we have the solar panels available now very inexpensively, and inverters and power electronics and smart appliances, but we are missing some kind of a standardized control system or management system. And that's what EMMA is intended to fill. EMMA will be a set of international standards that's openly available to anyone, and based on open source software that can be, it's not a product that I'm going to be manufacturing or selling. It's something for the world to use, and it's being standardized by the International Standards Organization and the International Electrotechnical Commission. There's a parallel concept is called electrification, and you'll hear this a lot, the new thing. But that means moving your energy usage at your home or your business entirely to electricity instead of other fuels. And but the important principle is don't run that electrification on coal or natural gas or oil or diesel or any kind of fossil fuel. It's a matter of the new and the old. The old structure is a top-down view that was created initially in 1900, and it's rather amazing to think that when we've only had electricity for about 130 years, although we've lived on the planet for a long time. The idea originally was centralized flow, generation and transmission, from generation to transmission to distribution to customer. It was a very capital-intensive technology. You had to have big coal plants, use natural gas, nuclear, big hydro. It took a lot of money. And there were big economies of scale in doing that in the beginning. But the technology has advanced since then. The new structure and technology is appropriate a bottom-up view, which is basically roughly begins in around 2000. 20 years ago, 23 years ago, the idea that it became economical to build equipment that was decentralized and localized, inexpensive mass market consumer electronics, solar PV panels, inverters, batteries, smarter appliances. This makes it scalable. There are no economies of scale anymore. A solar panel produces a certain amount of power, regardless of whether it's on your roof or in some large solar facility, solar farm. The concept is an alternative path that I'm suggesting is best for the future. But it is compatible with the existing grid, the way it's structured now. It's not a matter of we can keep what we have, and then we can start adding with the new technologies, and they can work together perfectly. Starting with individual homes and buildings, solar communities, microgrids, and storage. Available and inexpensive for solar batteries. As I mentioned before, these products are now becoming economical. But what it's been lacking, as I pointed out was the premises control system, how to manage all that, because it becomes important that you manage the energy on the premises. Previously, the power plants were designed to meet the maximum possible load. We don't have that luxury anymore. We can manage it more carefully and efficiently on the premises than we could before. So now we can move to this new approach, a generic home energy management system, sometimes called HEMS. We now have a version of that offering a version of that called EMA. So let's, but quickly before I go into it, let me make a side trip here with mention the role of the smart meter. Unfortunately, smart meters are not the smart grid. They were really developed in the 1990s. The AMI technology that's common today, it's called advanced metering infrastructure, was advanced in 1990 when we developed it, but it's not, and I was involved in that, but time has come and gone. So the meters are not the smart grid. The smart grid is still in the work in process, and that's what we're talking about today. The smart meters do not manage energy. They do not benefit consumers. They add unnecessary risks, safety risks, security risks, privacy risks, and radiation risk. Smart meters add unnecessary costs. They were only introduced really to eliminate jobs and to add capital cost recovery for investor-owned utilities. They do not integrate with renewable energy. They do not help that. And they are not a substitute for the smart grid or truly smarter energy, which is what EMA is all about. So what is EMA? EMA is an acronym for Energy Management and Measurement Application. It's part of a set of standards for what's called the HES Gateway, the Home Electronic System Gateway, which is an information gateway for your home that connects to preferably to optical fiber networks, but to any external network. And it's based on the EMA is part of that. It is developed by ISO and IEC, which are the top of the global standards pyramid, headquartered in Geneva, and they publish many of the international standards are published by ISO and IEC. And in this case, the two are cooperating. The IEC was created to standardize electricity in the beginning, back in 1907. The open source software that EMA is going to be using is really based on Linux and Raspberry Pi, Arduino. These are off-the-shelf products that high school kids can use to plug this together. So the idea is something that's simple that an open source market could develop around. A mass market, grid compatible, enabling technology, enabling incremental change to the new architecture of energy. The next generation, EMA replaces the smart meter. In other words, we conceived of it as a replacement for AMI, and it was next generation because it measures the original concept behind the smart meter was to use it on the premises, not to send the data somewhere else, but to use it to manage energy. But apparently, that proved difficult because of communication issues and stuff. But now all of those problems are solved. We now have high-speed fiber networks going all over the nations and the world, and we can actually do some of these things that we couldn't do back in 1990. There's no dependency on wireless in this system. Not that we can't use it, but we don't depend on it for anything because it's not as reliable as wired technologies like fiber and copper, Ethernet, and things like that. We do not rely, this system, EMA does not rely on cloud services either, on the internet. It can use it, yes, but is not vital to its operation. It can function entirely standalone if it needs to. It enables the concept of a microgrid. A microgrid is just a group of homes or buildings or campus that can operate without a connection to a larger grid if necessary, but it can be part of a larger grid, and that's commonly referred to as microgrids. They've been around for quite a few years, but now the idea here is to make it cheaper and more easily implemented. It provides semi-autonomous operation and sharing power within the local community if needed or desired. It augments utility services with or without solar PV. You could actually just use the management capabilities of EMA if you didn't have solar on a particular building or home, and it can provide grid backup, load shifting, and solve the duck curve problem, which I'll discuss in a moment. It can implement utility demand response services and other protocols that are used by utilities. It can charge car batteries and expedite the local or the growth of the electric car management and charging, because most people will be charging cars at their home or where they work. They're sometimes on the road. The duck curve is an interesting problem because it's what happens. This is a picture of it, and this came from the experiences in California with trying to put solar onto the existing electric power system. If you don't have batteries, you just feed the power directly that comes from your solar panels on the roof of your building into the power grid. You get this a problem that comes about. The more power you put in, that you can see the belly of the duck gets bigger and bigger. But you provide all that power into the grid, but you don't provide it at the time of day that it's mostly needed, because it's mostly needed in the evening. To the right here, you can see the head of the duck. You have a big problem there, because then you're using most of your energy at the later in the day when the sun has gone down. Well, the obvious thing to do is to put a battery in the system and store that solar. Don't put it into the grid at noon when the sun is shining. Just store it for a few hours and use it in the evening when you really need it. And this duck curve problem has been limiting the capacity of local power grids to maybe 15% of the load before it becomes overloaded during the day, and still has a problem at night. So it's what is called net metering, which is a technique of feeding all your power into the grid and not having a battery. This is limiting the deployment of rooftop solar. So why don't we just put a battery with it and solve the problem? That's the idea, anyway. Here's a depiction of the overall grid. You see on the left, you see the large generation facilities, wind, could be solar farms, could be power plants, coal plants, nuclear plant, any form of large-scale generation. That's the way the grid is structured today. But then we move to the right of this picture, and we see that it in the far right, we have in the lower right, we have the picture of a microgrid where rooftop solar is integrated with the newer buildings or older buildings that have been refitted, can actually fit nicely with the existing grid, because they don't, if they have batteries, they don't overload the grid, and they can still work together. So the traditional hybrid, we call this a hybrid grid, using the new and the old integrated together, and possibilities of building microgrids. So to look at the structure of this in the individual home, here's a picture of a conventional system that causes the duct curve problem. This is the solar panel on the roof on the right-hand side of the picture, and it has a inverter which changes the solar energy into DC power, which is then or into AC power. I'm sorry, and feeds it into the power grid. And then on the left side, you have your various appliances. So when this works, provides power to the power grid, but it is limited by the duct curve problem. And so that's not the solution, but this is the way it's being done up until now, because we didn't have the batteries available, and we didn't have the smarter inverters that are needed. So in the next slide, we should be able to see the future, where we have at the lower middle of the house, we have the EMA management system, and it's connecting to all these different elements. We have the solar panel supplying power again, but a little bit smarter inverter that can actually charge a battery with DC power, and not just and it can provide power to two circuits in the house. One is a priority circuit at the top, and the other is the conventional circuit at the bottom, the main circuits. What happens when there is a power failure, and either the solar system or the battery system or both feed the power to these priority circuits first and disconnect the power to the grid, so that it becomes a standalone system that isn't necessarily powering everything in your house, but certainly powering the priority circuits, things that are plugged into the upper circuit that goes to the left of the picture. And the electric vehicle could be on either one of those. That's why there's a dotted line there. It depends on your situation. So this requires the energy management system, the EMA system, to orchestrate all of these moving parts. That's what's new here. And we have appliances now that can be controlled remotely, particularly hot water heaters, things that hog a lot of energy. With hot water heaters, heat pumps for heating and cooling. Heat pump could be on the priority circuit if you wanted it to be. But you can reconfigure this in any number of ways, and that's why we have a flexible system. The standards for EMA are all intended to be customized to different applications and configurations of home appliances and home use and generation. So this is basically the diagram of how it works. The this is where we are trying to get to, this picture. Now, just to summarize, the EMA functionality is energy management and measurement application. The functions are, some of the functions that it's going to do for you would be, or that you can program it to do, or you or whoever's doing the installation. I would anticipate that solar installer dealers would pick this up as a market opportunity to provide this service to their customers, so an ongoing basis. The load balancing, appliance control, inverter management and monitoring, EV charging and management. That's going to be depend very much on individual needs. Grid conditioning and management for the home. Normal. It has three states. The three basic states of operation. One is normal connected grid, when you're just augmenting the existing power grid, and taking some of the load off of it, and the second state would be disconnected when the grid has failed, or if for some reason you've disconnected from the power grid. And that's a second state of operation. And then the third state would be when you're actually not when you are sharing energy within a local community, but not connected to the larger power grid for a period of time or indefinitely, to maintain operation, some level of operations for everybody, so they can live in their houses comfortably. It will carry out demand response in cooperation with utilities, and it can support virtually any form of demand response. It would work best with fiber network. Fiber optic communication is fast and almost unbelievably fast and reliable. And that's what we anticipate having, although it would work with any form of broadband communication. Microgrid management, that's another energy management function. We'll be managing the local microgrid in cooperation with other homes. And the energy measurement functions of EMA are the standard AMI metering and utility functions that are done by metering today, plus the solar production measurement and the battery status measurement and performance and power quality measurements. And this is an important one here that people aren't used to having. It will measure power factor, in other words, the efficiency of what's of your home and how it's working, and point you to ways to improve that efficiency. And harmonic emissions, also called dirty electricity, can be eliminated because it will be EMA will be monitoring in real time the harmonic emissions conducted and possibly radiated emissions of electricity system in your house. So then here, just as a recap, a few basic points. Inverting to summarize what I've said, the EMA view is to invert the grid from take a bottom-up view rather than a top-down view, a view of the grid from the home or building as if it were a yacht or a boat or a RV, starting at home instead of looking at it from a power plant downward. The premises architecture we talked about is the solar and storage, and the key factor, the key thing everybody is going to be needing in the next few years is resilience. In other words, the ability to recover from severe weather and severe other severe conditions that may reduce the functioning of the electric power system that we have. This means floods, fires, wildfires, hurricanes, virtually anything that can happen because you're being able to support local operation of your home without necessarily connecting to the grid. You can generate the principal takeaway here is to generate electricity as close as possible to where it's used. That's the most efficient thing to do. Remember that the big transmission lines, the high voltage distribution or high voltage transmission system, can take away 10 to 18% of the energy. Just transmit it. That's a big hit.
You mean the transmission losses?
Say again? Oh yeah, transmission
losses are up to 18%.
But in some cases, it depends entirely on the configuration. But I have usually I'd say a good number would be 10%. The missing piece here again is the EMA control system, and EMA is is an approach to solving that problem. There are other control systems on the market today, but they're proprietary. EMA is free for everybody. It's open basically to anyone to use. Electrification is the new thing, but don't run it on fossil fuel. The old is now, the technologies are new, but they can fit nicely with the existing power grid, so there's no conflict. It's not either or. We can phase in the new system as fast as you need to or want to. Consumer electronics is basically replaces the traditional industrial economies of scale that the electric power grid began with. And the key words here are sustainability and resilience on your roof. Keep in mind that electric vehicle charging can cost you, it can double the power consumption of your house or a building from what it would normally use, just to be able to do that, because you're putting a lot of power into those batteries.
If you're heating, unless you're heating with electricity, of course, as we do here.
Yeah, well, you could, yes. The heating with electricity can be vastly improved by the use of heat pumps. The heat pumps tend to be 3 times more efficient than resistive electric heating. And that's, there are many, in fact, new water heaters are being introduced now that have heat pump heaters instead of resistive electric heaters. They still run on electricity, but they operate like a refrigerator. And they're far more efficient. And who can do this now? Well, investor-owned utilities are very slow to be able to do any of this because of their economic business model. But munis and co-ops can certainly do it. They are owned by their own customers, so they can.
Munis, you mean municipal utilities?
Yeah, municipal utilities and co-ops, or what they call rural electric associations, are owned by their customers. So they don't have to generate profits for Wall Street. Optical fiber enables this, and it's a nice synergy between the optical fiber for internet access, but now for also energy management. And that seems to be a big trend in the world today. And the concept of energy democracy, in other words, the investor-owned utilities and public utilities commissions that govern them are basically parasitic institutions, and we don't need those anymore. The key slogan that I like is democratization, decentralization, and decarbonization. Those all go together. And there are hundreds of millions of people who still do not have electricity, and they would start with something like this, and they would not need to start out with a big centralized power plant. Because this can be implemented on any scale. So I would see Emma being used in the developing world quite widely, because it could empower those people quickly. So there are some references to this. I mentioned before, there's a book that I wrote in 2012, Getting Smarter About the Smart Grid. It's really about the use of the smart meter and what the shortcomings of that approach were, and where it needed to go. It was forward-looking. Now we had an article. The second item is easily found. It's from the Solar Today magazine, titled Intelligent Energy, Solar Homes and Microgrids of the Future, that was published in 2020. And that's kind of the manifesto for Emma. And then more recently, I did an article that talks about energy in the global scale and what's been holding back solar energy and why. Because we keep fumbling around looking for all these solutions with nuclear power and hydrogen fusion, and like we already have hydrogen fusion. We don't need a new one. We have it nicely located 93 million miles away. We don't need to we have a nice fusion reactor. We ought to make use of it instead of trying to reinvent it and centralize it somehow. The and there's also a review I wrote of the history of the electric power system that you can called Power Struggle. That was the name of the book, written a number of years ago, but very gives you a wonderful historical perspective on how electric power came to be and developed. Even though it was published in 1985 or something like that, it was very important to understand the history of how we got here. So I think that wraps up my talk. I'd like to take questions or comments.
Yeah, well, I'll be asking the questions today and commenting. We have a particular situation, of course, in Quebec. We do own our utility. Hydro-Quebec is public. The profits go to the government, so it pays for our schools and hospitals, they say. And we have probably the cheapest and cleanest energy in North America, if not the world, with hydro and a lot more wind turbines in recent years. But the average cost of electricity is 7 cents per kilowatt hour, 7.5. But they add taxes. But so it's getting close to 9 cents and 10 cents. So there's a scientist at Natural Resources Canada, a physicist, who told me actually PV, now photovoltaics, is cost effective compared to Hydro-Quebec's power if you look at the 30-year service life of these solar panels. Now, I want to thank you for this great talk. It's really interesting and timely to discuss about local control because even in Quebec, where electricity is cheap, actually it's an impediment to energy efficiency and management. But even in the US, where the cost of electricity has gone up a whole lot, I see that people really resist these utility programs to manage and save energy. So I'm wondering if you think that large-scale utilities will be interested in EMA. And I'm curious also because you say that it's going to replace the smart meter. And I'm trying to understand, I understand that EMA is an energy management and measurement application that you can use in your home, but you're saying that utilities can also use it to measure your consumption?
Yes, they could in the conventional way. In other words, the EMA will support the old AMI standards that that are used in all the smart meters, if they need to. But what they do the smart meters do not do, EMA will manage the energy on the premises with that information. Whereas the smart meter concept was to transport the information to the utility and then possibly send it back, although it's been found that the route back doesn't work. It never is virtually unused at all. So and it's such a staggering task for a utility to try to measure your water heater and your toaster and control millions of devices all over it. That's just not feasible. It should be done on the premises, and the utility shouldn't have to do that. But they could send signals as to the EMA system saying what the condition of the grid is and how much people need to conserve, and then the EMA could handle it from there. Because EMA knows what's in your house, and they don't need the power utility doesn't need to know all that.
Well, we do have an application that a subsidy of Hydro-Quebec called HILO, H-I-L-O, is asking people voluntarily to participate to shift the loads, that is, reduce their consumption during the peak periods in the winter when it's really cold. It's between 6 and 9 a.m. and 4 and 8 p.m. But again, very few people are participating. Here we show the first microgrid in Quebec in Lac-Mégantic, where there was a train derailment, destroyed the downtown Lac Mégantic. And so they're testing a PV microgrid, but it's all wireless. Explain again why wireless is not the best way to do it. Is a lot of people would say wireless is a lot cheaper than have cables all over the place.
Well, that's not really true because the wireless requires cables also. All the wireless systems, all the your phone, smartphone networks and all that, 5G, 4G, those all use optical fiber to all those sites, and they're trying to put in more and more sites closer and closer to people all the time with the microcells. So that's kind of a false representation, I think. And wireless is the main problem though with wireless is that it uses at least 10 times more energy overall than a wired system, because you're blasting these transmitting information in all directions rather than focused on a particular down a wire or a optical fiber. So it does take there's studies that have been done that show that there's at least 10 times loss of energy, and but all methods have drawbacks. I mean, there's nothing that's free, but you have to consider the embodied costs in the system too. And the problem with wireless is that it's all constantly changing and going obsolete and being replaced. And the same thing with the meters too. And
Yeah, how long are they supposed to last? Because it's funny, you published your report in 2012 on smart meters. That was the year Hydro-Quebec began deploying the $4 million, actually 4 million smart meters were installed. And they replaced nearly, actually, it was 300,000 of them were replaced. And I was wondering, do they last 20 years, 15 years? And what are they going to replace them with? Is Emma going to come on board soon?
Yeah. The old analog meters would last 50 years. There's no reason, but the new ones, that it's cheap junk, it's a junk electronics, and it is designed to wear out or be replaced. And there's this thing called planned obsolescence too. The money is to be made by the manufacturers and the utilities by replacing them and making the ratepayers pay for it. So I suspect that the life of a meter is down below 5 years. No matter what they say, oh, it can last 20, but that's not been the experience. They are broken. I know other cases just like you described where they have to be replaced. One in case here in Colorado where it was replaced in a whole city did them and had to be replaced in about 2 years because they
more
were.
Than 90% of them have lasted over a decade. But you think in the next decade they're going to have to replace them all?
Well, they're already obsolete. They put them in here in Denver, and now they want to do a new generation because they want to do time of use pricing in the meter, and that's their excuse. So they can make another $500 million worth of profit for the utility.
Do you expect them to go with wire meters someday?
No, they don't. Well, they don't want to because they make more money off the wireless. They have the towns. They're putting in optical fiber, but they don't want to use that. The power company has a competitive attitude toward, except in the case of rural electric associations and co-ops, and maybe some munis. They're competitors. They don't want to use some competitor's product.
Well, in Quebec, there's no competition because we have 2, 4, 6, 8, 10 municipal utilities. They're tiny and they all buy the power from Hydro-Quebec, but they have their own programs.
Is Hydro-Quebec putting in optical fiber for all of its customers?
Not Hydro, the cable companies are putting them in. We're doing our recording.
Well, that will end up costing more, though, I think.
Our recording actually is powered by our battery. My office is powered with a lithium battery, and I have photovoltaic panels. And the cable service is fiber optics and coax, and then Ethernet throughout my house. But I'm wondering, do you think large-scale utilities will go for all these solutions? you're proposing?
No, I don't think, because they don't make enough money at it. You have to keep in mind that the large scale utilities, investor owned utilities in particular, have to make a profit. And you might say that Hydro-Quebec is in a different position, but because it's owned by the state, but it's operated like it is essentially an investor-owned utility, because the investor is the government, and it's a profit. It has to make a profit.
Mhm. Well, we do have the programs to subsidize batteries and photovoltaics here. It's a federal provincial program, so it's a Canada Greener Homes grant and also loans. And Renault Climat in Quebec is where we sign up for these. And again, I don't think there's, most people don't even know that they can get $1,000 for their solar panel installation. We've been talking about, distributed power, local power for many years, but it's not really happening here. Is it happening? I know that, like in Texas, they have lots of solar and wind power big time. But do you think that your solution is only going to be taken up by municipalities and co-ops?
Well, for now anyway, because the basic problem, I think, is profit. These are, Texas, for instance, has all this wind and stuff, but the wind is all privately owned for-profit corporations, and that's why they like large wind farms, large solar farms. I'm not a fan of either one of those. I'm not a fan of offshore wind. I'm not a fan of wind turbines, because it basically is a centralized power plant, just like a coal plant or a nuclear plant. It's not going to be a benefit to the consumer. It's going to be benefit to the stockholders.
So do you think that in a few years, the governments will be subsidizing, even giving more generous grants to put PV panels on rooftops?
I'm not. They are, well. There's some of that, yes, because they're realizing that they can't. The power grid, the way it's structured, can't can't have the reliability that it needs to have, and the cost is going to be high, because people have to pay for the retiring the old coal-based or the centralized power system, and then they also have to pay for the new stuff, the new solar and wind, and that the ratepayers can't bear that. So there's going to be a political problem there.
Yeah, well, we're lucky we don't have nuclear or coal, but it's going to cost a fortune to upgrade the grid. Hydro is negotiating with the Crees to actually optimize the existing hydro plants up north to increase their power, but that's going to affect the hunting grounds, and more rivers will risk overflowing and what have you.
Yeah, it's an environmental problem. What we're finding is, for instance, the West Coast of the United States, Washington State, Oregon, and California, they're having to tear out hydro facilities because they have the environmental consequences have been so terrible. They've lost the salmon population. There's an article in the New York Times yesterday about the salmon and they've had to put a moratorium on all salmon fishing off the west coast of the United States, because the dams have destroyed the ecosystem. So they're in the process of removing 5 dams on the Klamath River right now, starting that process immediately.
Yeah, new dams is definitely going to be the last resort for Hydro-Quebec, but they want to increase their production by 50% by 2050 to decarbonize our economy, help New England decarbonize. They want to export to Maine and New England, Massachusetts, and our electric vehicles. They want to ban new gas vehicles by 2035. But we're really wondering, how are we going to do it? And tell me about,
I'd say,
how does Emma fit into this? And do you think, are there major electronic industries interested in Emma?
Well, we don't know yet. We're still building it. So we're not advertising it until we have it. We're in the prototype stage right now.
Okay. When
And we're
will it be available? The protocols.
well, I'd anticipate we'd have demonstration sites later this year. Hopefully, we're running in several locations in Canada and in the United States. The beefing up the hydro facilities and improving their production is probably a good thing to do, but keep in mind it depends on the availability of the sustaining those power transmission in the face of severe weather that we're going to be having, and we're having interruptions all the time now. And more, and they not just from weather, but people attacking these facilities. I mean, it's like strange, we have there's a vulnerability to the whole transmission system and Emma is about managing energy more carefully on the premises where you're using it. So that's the concept. We can certainly improve the efficiency of the centralized system. Yes, even without the solar panels, but and putting batteries is a big thing, because it gives people resilience. They can run their refrigerator when the power goes away because the transmission line got blown down by some severe storm or forest fire. So, that's an important thing to keep in mind. That's a benefit. I'm not saying they shouldn't be improving what they have and continuing with it. As I say, the old grid and the new grid are completely compatible.
Mm-hmm. There again, for Quebec, we're lucky we don't have the wild forest fires that you're having down south, and there's heavier rainfall, which is good for the hydro dams, their reservoirs. But I think we will. I was fearing that we wouldn't be able to record today because we have a major ice storm. I'm glad that we were able to do it, but that's really, we're going to have to see. Actually, the big problem with Quebec increasingly will be the peak loads, where hydro has to import dirty and expensive power from other provinces or states. And but I was talking to a vice president at Hydro-Quebec who said that they could not impose the peak rates at time of use because 80% of our homes are electrically heated. The majority of Quebecers are tenants. They don't have any control over the insulation of their building. So I'm really wondering how Emma could help utilities to really encourage people to shift their peak loads.
Well, one of the best things they could probably do is to replace a lot of those all the resistive heat with heat pumps. That's a new technology that is now moving very rapidly.
Yeah, they're subsidizing.
And that would give them a 3x benefit on the heating anyway. And the Emma would help manage that and make sure there's no mitigate the peak load problem on the premises, at the premises site, where you actually have control over individual loads in your house. You don't have to have your water heater come on at the same time as your heat pump. You can orchestrate those so that it flattens the load.
And in conclusion, do you think that these new technologies such as Emma and cheaper photovoltaics are really going to shift the energy industry as the internet did?
Well, that's what we're hoping. We're not saying that you can change big institutions. It's very hard to change big institutions, and the structure of the power system throughout North America and the world is pretty frozen, in the technology arena. But the new technology can come in and actually, by being cheaper and more efficient and delivering value, can actually change that system. And it's better than trying to change it through politics or regulatory agencies. That's really not going to change anything really or much. But the new technology that can actually change things.
Mhm.
That's what happened with the voice over IP. When the Bell system was
Yeah.
dominant, we had all kinds of litigation, and we had new laws passed, and court fights, and we tried to dismantle AT&T, but it kept growing back. But then all of a sudden, along comes the internet technology, which takes it inverts the structure of their voice network and their data network, and actually within 5 years sweeps through and essentially replaces it all with the internet.
Yeah, that was the end of the Bell Canada monopoly for sure. Well, Tim,
And that,
it was really a pleasure, fascinating stuff, and we'll invite people to contact you over the web. And in closing, a message for Canadians.
oh, well, think local. Think local. That's where you live and work, and that's what you need to keep working, keep maintaining, and the um, and you have a system that works now, but think about the future and think about the problems you're going to be facing in the coming years with climate change.
Mhm. I like your term energy democracy and local control, power to the people.
Yes, or power. Yes, power from the people.
Hmm. Tim Schoechle, thank you very much.
All right. Thank you, Andre.